Good morning. Welcome to lecture 2. Hope you have watched lecture 1 and read the file PFR1 that I uploaded on Canvas. It is very important to read this document carefully because it lays the foundations for the entire course. So as we have seen in the last lecture, we discussed different properties of substances. So to quickly recall, we saw the definition for physical thing. A physical thing is something now. It is something now, but can become something else. So this is the potency. So now, with this definition in mind and the different types of properties that we have seen, quantity, quality, etc., the intrinsic and extrinsic qualities, and what we discussed about measurement, let's go into chapter 1 of Pedrotti and Pedrotti. Once again, we will be using Pedrotti and Pedrotti, third edition, for this course. So in the first chapter in this book, nature of light is discussed. So let's look deeper into nature of light. So to do that, first let's go back to the imperiometric method, which was applied to motion or locomotion by Newton. So what is the imperiometric method? Imperiometric. So in imperiometric method, we observe the physical reality and express this in a mathematical way. For example, if you were to say F is equal to ma, you are expressing the laws that you see in physical reality in a mathematical form, and that's a modern way of doing physics. And Newton applied this imperiometric method for the first time to laws of motion, and that's how you know Newton's laws. So when Newton was expressing the universal law of gravity in a mathematical form, you know that F, the gravitational force, is G m1 m2 by r square if you have two objects, let's say m1 and m2, that are separated by a distance r. So here now the thing that where Newton did not completely understand, or what Newton did not completely express, is the idea of this gravitational field, or how say mass m2 feels the force from mass 1. So this action at a distance was very bothersome in the early days, because they did not understand what space was in a correct way. So for example, if I remove this mass 1 from the picture, mass m2 does not immediately feel the effect of me removing mass m1. It takes some time for the information to go from this point in space to where m2 is. So somehow in mechanics courses, you're taught that space is nothingness or emptiness, and the idea of abstract mathematical space is projected onto the physical space. So in reality, as Einstein's general theory of relativity describes it, if you have a mass m1, it is somehow changing the space around it, right? And these changes in the space propagate in space, and same thing with M2, it is also changing the space around it. Right. So any object that's massive, any massive body affects the space around it. Space is not nothingness. Space is extension. So when I place an object at a particular point, it changes the space around it, and these changes in the space in one part of the space propagate to the next part of the space, and as these changes propagate outwards, the effect goes down as 1 over r squared. So that's what a field is. A field is basically you are changing the space around, perturbing the space around an object. So if you have a mass, the gravitational field is perturbing the space, and it is this perturbation in the space that mass m2 feels. So if I remove mass m1, for example, it takes a while for this information to propagate to mass m2, because as soon as you take this mass m1 out, the changes in the space that it has created do not disappear immediately. It takes time for this to propagate from where m1 is to m2. So that's what you have to bear in mind, that space is not nothingness or emptiness. Instead of just massive bodies, if you have a charged massive body, say if I have a charged massive body q1, right? If this has a charge and I have another charge q2, then you have an electric force, right? kq1 q2 by r square, just like the universal law of gravity. Here also the charged massive body, or simply the charge, is creating perturbations, is perturbing the space around it, and it is this perturbation that the other charge q2 feels. So electric and magnetic fields also perturb or disturb the space around them, and that perturbation in space propagates outwards, and as it is propagating outwards from one part of the space to another part of the space, it gets weaker as 1 over r squared, and that's how we have inverse square laws. So the thing to remember, the most important thing to remember, is space is not emptiness or nothingness. As we discussed in the last lecture, can nothing exist? Nothing by definition is non-existent. So it would be wrong to think of space as something that is non-existent. So all these gravitational, electric and magnetic fields reside in space, and space has extension. That's a property. Quantity is a property. So space, it exists of itself, and it has extension, which is a property, and also it has fields. For example, gravitational field, electric field and magnetic field, they reside in space as perturbations in space. So fields are also property of space. And you can see that from here you could say that light, which is nothing but electromagnetic radiation, is also a property of space, right? So light is a property of space. So once again, please note the difference between substance and properties. Substances can exist of themselves, but properties can only exist in the substance. Now imagine light without any extension, without any space, right? So it would be hard. It can only exist in space as a property. So now let's take a look at the wave-particle duality. Wave-particle duality. So here we need a brief discussion on quantum mechanics. So wave-particle duality basically is often misunderstood, thinking that it is an electron or a photon is a particle, and it also behaves like a wave at the same time. So that is not true. To understand what the wave nature really means, you need to understand the concept of ensemble measurements. So in an ensemble measurement, for example, if you were to repeat the double slit experiment with electrons, so I will upload a link on Canvas where you can watch a recorded experiment of electron double slit experiment from Hitachi. It's very important that you watch this video to understand ensemble measurements. I will describe what's in the video here, but you should nevertheless watch the video. So in a scanning electron microscope, you have a filament. For example, you have a filament like lanthanum hexaboride. So let's say this is a lanthanum hexaboride filament, and from here you can extract electrons by field emission. So you can have electrons coming out of this filament. Now if we place a slit here, a double slit here, and then there is a screen here, right, then there is a screen here, an electron coming out of this filament could either go through slit 1 or slit 2 and fall on the screen. Now if you want to see the double slit fringe pattern, you have to wait for a million or so electrons to fall on the screen. You don't see the double slit pattern with 10 electrons or 100 electrons. As you do this measurements, you will see in the video that I will upload, you will see that the first electron falls on the screen somewhere here, the second electron falls somewhere here, the third electron somewhere else, and you won't see any pattern. It looks random, but as you do more and more, as you see more and more electrons go through the slits, then you would see that a pattern begins to form. You would see a dark and light fringes. So these would become fringes. You would be able to see these bright and dark fringes after several electrons, billions of electrons fall on the screen. You don't see it with 1 electron, you don't see it with 2 electrons, you don't see it with 10 electrons. So this is what a statistical or ensemble measurement is. So it is not that it is 1 electron that is being particle and wave at the same time. Here, the wave nature comes from an ensemble measurement. It's not a single measurement on a single electron. When you observe a million electrons go through the slits, they somehow form this pattern, and that's what you are expressing as a wave, right? And from here, you come up with the idea of a wave function. So the important thing to note here is wave particle duality doesn't mean that an electron is a wave and a particle at the same time in the same way. That's against the principle of non-contradiction. That is not the case. When you do an ensemble measurement, you would see the fringe pattern, and from there you deduce that that there is a certain probability of an electron to be found in a particular place, and you express this probability amplitudes as a wave function, for example. So this is a statistical thing. So bear that in mind. When we say wave, we are deriving that wave nature from statistical measurement, not 1 electron. Right? That's what we mean by the wave function. That when you do an ensemble measurement, there is different probabilities for an electron or a photon to be found in different places. So that said, we can now, because this wave function is probabilistic, we can now look at a de Broglie wave particle duality, that when you do ensemble measurements, they can behave like waves. So here, when we are talking about electrons, this is called the first quantization. which means that after you look at multiple particles, that is particle like electrons, um, when you do an ensemble measurement, they look like a wave, right? So you're treating a particle like a wave. And light has to do with second quantization, where you're looking at light waves. Light is considered to be waves, but it appears to behave like a particle. That is the second quantization. So De Broglie's um, wave particle duality, basically he states that the wavelength lambda can be related to momentum as lambda is equal to h over p, right, where h is the Planck's constant, right? And in case of light, you will have to bear in mind that the relativistic equations whenever you are talking about light, because you have a speed of c for any photon, so you have to bear that in mind. So that's what wave particle duality is about. Lambda is equal to h over p. And bear in mind that all the measurements, whenever we talk about wave-like behavior, we are talking about ensemble measurements. Right? So that said, now you know that the electromagnetic spectrum, you know that all types of electromagnetic radiation, they all travel with the same speed, that is speed of light, which is c, or 3 times 10 to the power 8 meters per second. And in case of electromagnetic spectrum, we have different types of waves. So if I were to write based on the wavelength, you have gamma rays somewhere over here, right? Very low wavelength, right? So it could be something like 10 to the power minus 14, right, meters. And then you have X-rays, and somewhere here you have UV, which is roughly a little bit below 400 nanometers. And then you have the visible light, which we know, and which our eyes are tuned for, 400 to 900 nanometers. And then you have IR, and then you have microwaves, even longer are radio waves, right? And you can also look at this, instead of the wavelength, you can also use the frequency, right? So if I denote wavelength by lambda and frequency as nu, then you know that nu lambda, frequency of an electromagnetic wave, times the wavelength lambda, is equal to c, the speed of light. So if I look at it in terms of frequency, the wavelength is something like 10 to the power minus 14 meters. So the frequency is something like 10 to the power 22, 10 to the power 22 hertz. And if you look at the visible radiation, it would be somewhere around 10 to the power 14 to 10 to the power 15 hertz. Now that's the frequency of visible radiation. So we can also calculate the energy. We will talk more about these things later in the course, but an energy of a photon is given as Planck's constant times mu, or the frequency. We will see how this energy is equal to h nu comes about when we look at dipole radiation later in the course. The frequency has to do with how fast a dipole is vibrating or oscillating, and the faster it oscillates, there is more energy that you can produce. So energy is proportional to the frequency, or we would see that energy is equal to h nu, right? So if you have say a light bulb or a laser that has a known power, certain power, right? Power is energy per unit time, right? So if you know the power, so energy is in joules, or in case of light it is often measured in electron volts, and power is in watts, right? Joules per second. And so if you know the power, then you can calculate the number of photons as the total power. For example, if I have a laser, a helium neon laser, it has a particular wavelength, and at that particular wavelength I can know the frequency, so I can know the energy of a single photon. So I can write the number of photons as power divided by energy per photon. Energy per photon, right? So with this, let's do an example problem that's in the textbook in the 3rd edition. So we are going to look at example 2, which is on page number 10 in chapter 1 of Pedrotti and Pedrotti, right? So so here we have an electromagnetic signal of frequency 100 megahertz, and the power is given to be 6.63 times 10 to the power minus 16 joules per second. Right? So the first thing we are asked to calculate is the wavelength of this signal. So you're given the frequency, so you know that nu lambda, frequency times wavelength, is equal to speed of light, which implies wavelength is equal to c by nu. So c is 3 times 10 to the power 8 meters per second. And you have 100 megahertz, which is 100 times 10 to the power 6 hertz. And if you calculate this is 10 to the power 8, so this cancels this, so you have 3 meters as the wavelength, right? And now we can also calculate energy of a single photon, because E is equal to h nu, right? So if you do that, you will see that energy of a single photon here is roughly, the Planck's constant is 6.63 times 10 to the power minus 34 joule second, and the frequency is 100 megahertz. So that gives you 6.63 times 10 to the power minus 26 joules, right? That's energy of a single photon, per photon. Now if you want to calculate the total number of photons, then we do the power that we have divided by energy per photon. So the power we have is this, 6.63 times 10 to the power minus 16 joule per second, and energy per photon is 6.63 times 10 to the power minus 26. So you can see that we have around 10 to the power 10 photons per second. So notice that this is joules, this is joule per second, so you have per second left over, so you have a number of photons, right? So what you can see here is that each photon contributes 1 part in 10 billion to the total power. There are 10 to the power 10 photons. So when you have so many photons, right, even for a weak signal that has 10 to the power minus 16 joule per second, which is very, very weak, even for such a signal you have 10 billion photons, right? So that's why you don't see the particular nature. You see it as a continuous stream of energy, and not grainy or pixelated energy, right? So with this we will stop this lecture here. We are not going to get into the radiometry, that is section 4 in chapter 1. In chapter 2 we will start with geometrical optics, right? And bear in mind that we're just getting introduced. This may seem easy and straightforward, but it is essential to go through these foundational principles. Bear in mind that space is not nothing, that fields exist in space, and they're in fact a property of space, and so is light. And in addition to that, it's also important to remember principle of non-contradiction and what wave nature really means, that it comes from an ensemble or a statistical measurement and not from one single measurement. So it's important to bear those in mind. Thank you. We will meet again in lecture 3.